right. And we are recording. And before I introduce our amazing speakers, I also want to let you know that if at any time you have any questions, what you can do is at the bottom of your Zoom screen, you will see a little box that says Q&A. Any questions you type in the Q&A box, myself, Joe, and Rajan will be able to see those questions. And at 10:40, we will break for Q&A. And at that time, they will be able to answer your questions. So without any further ado, let me go ahead and introduce Joe and Rajan. So today we have Joe. Joe heads the team that provides key value storage and messaging systems for all of Verizon Media. Verizon Media is a combination of Yahoo, AOL, Huffington Post. Joe has led the development and operation of multiple large-scale distributed systems, including Pulsar, while at Yahoo, now Verizon Media. Prior to joining Yahoo, Joe was the architect for database kernel storage and recovery at Sybase. He is a member of the PMC of Apache Pulsar. Joe is well-versed in the development of Pulsar from its very inception, which is why today is very exciting. Its growing pains to a large-scale system and operating at scale in production. Joined with Joe is another person who has been very involved with Pulsar since the early days. Hello, Rajan. Rajan is a principal software engineer at Verizon Media, working on messaging and distributed key value storage technologies. His interests lie in building reliable, scalable, distributed data processing systems. He is a committer of Apache Bookkeeper, a PMC member of Apache Pulsar. He is a lead developer of Pulsar within Verizon Media and has spent several years developing Pulsar in Yahoo before making it open source. Thank you both so much for making the time to present today. I'm going to go ahead now and mute myself and hand it over to you. Rajan, do you want to take us away?
Yes. Good morning, everyone. My name is Joe. I've been involved with Pulsar over 6 years now, led the development of it, open sourcing, and ongoing development of it within Yahoo.
Hello, everybody. My name is Rajan Dhabalia, and I'm a principal software engineer in Verizon Media.
So today we are going to cover a few things in our talks about some sort of background and use cases that we originally built Pulsar for, and then we are going to talk about our benchmarking and production provisioning models, which is important that if we're not doing this for, just for bragging rights, it's what we use to provision our hardware and our capacity. And Rajan is going to cover some of the intricacies and internal details about how Pulsar does with these use cases and how we run these benchmarks. And then we are going to finally go over some large use cases which we migrated off from Kafka to Pulsar, and some future directions we have in mind for our use cases. So originally Pulsar was developed to serve some particular business needs within Yahoo. That is to relieve developers of the pain of running message brokers for every application within their own teams. So so it's meant to be, run as a hosted, system for the entire company or organization. And, because of the requirements that Yahoo had at that time, that is, we operate in multiple data centers, serving latency is very critical in terms of couple of milliseconds in some use cases. And also the fact that a message bus was required for other low latency systems. So when you have a low latency system that is already running, and that requires a message bus of even lower latency, okay? And most of these applications are mission critical applications, write availability is paramount, and it runs at very large scale across the world. So these were the primary design considerations behind Pulsar, that it should operate within these constraints. So given all that, like how do we actually, set up systems and run them, right? What sort of benchmarking do we do, and how do we provision hardware to meet these needs, right? A lot of that is constrained for us because we buy hardware in bulk. We can't pick and choose what we want most of the time. We have to use what is available. Most of it is commodity hardware, which and we run at such a large scale that machines fail all the time. Now, most messaging system benchmarks works fine, and they have very promising numbers because data fits in memory and there is no disk I/O in the critical path. Everything is hunky-dory. Messages come in, flows through RAM, goes out to the consumers, and that's it. But that's not how real businesses run, right? In real businesses, there are applications that run slow. Applications can have outages. They want to go and replay history, So these benchmarks have to reflect, what real production workloads look like. And most of what we are going to talk today is under those conditions. And it matters a lot because if your benchmark does not reflect reality, the numbers you see cannot be really used to provision hardware, right? And the second factor we really had to consider is cost. What does it take to scale the system up and down? What does it take to scale the system in terms of fan out versus retaining data for a large amount of time? And these are different dimensions across which cost matters, right? For us, we prefer that we don't have to provision storage unless explicitly required by storage, because storage is far more expensive than compute, 4 to 5 times more expensive, right? So these are the considerations we use when we provision hardware to production, right? So we benchmark for those scenarios and across these dimensions. And why does it matter? It matters because of the different data paths you can have, in a real world work case, right? Let's look at a typical data flow path in the application. And producer that produces data produces a message. It gets sent to the Pulsar broker. The broker persists it in 2, or if you really need it, more storage nodes, right? The storage nodes actually persist the message. They write it to the journal device. They flush the journal device. The operating system acknowledges the flush. And then they send it back to the broker. And the broker actually waits for 2 acknowledgements to come back. And only then it acknowledges to the writer, hey, I have persisted this message. And only then does it send to the consumer this message, right? Now, there are different ways you can tune these knobs. And a lot of benchmarks you see out there play with these knobs. You can just send these 2 copies over the network and say, okay, fine, that is a setting, and that you'll get very good numbers out of it. You can send the message to disk, but not wait to flush it, right? You can wait for 1 ACK from 1 storage node, and then act to the writer, right? And depending on how you configure this, you'll get wildly different numbers. So what we are going to talk today is about persisting it, waiting for these 2 acts, and then acknowledging. We're also going to talk about the real world scenario of cold reads, because cold reads don't get messages out of cache. They have to hit the disk. And those reads are always in competition with the writes, data writes that is going on in those disks. So if you run a benchmark without cold reads, you'll get a totally different number. But you cannot use those numbers to set up a production system. In a production system, these things happen and they do matter. And that's why the numbers we are presenting today is based on real workloads where we wait for 2 acts for persistence and we have cold reads going on. And Rajan will walk you through the details of how Pulsar does it and how efficiently it does it with all kinds of hardware.
Thank you, Joe. Hello, everybody. My name is Rajan Dhabalia, and today I'm going to talk about Pulsar's journey in Yahoo, how it's been developed here and then evolved over the time with new emerging storage technologies. And we'll also talk how efficiently Pulsar has adapted those technologies time to time. However, in order to understand Pulsar's journey with those different storage devices, it's very important to understand the architecture of Pulsar storage, which is the Bookkeeper. Bookkeeper design is based on write-ahead logging approach to support faster transactional update and recovery. Write-ahead logging is an old technique used by database system for a long time. And based on this technique, Bookkeeper maintains two forms of persistent storage. First is a journal, which keeps appending incoming individual transactional updates. Journal writes incoming messages coming from different topics to a journal file sequentially. So journal is an append-only structure, so it helps Bookkeeper to get a higher throughput with low latency. And the second storage is entry log, where Bookkeeper persists ledger data, and Bookkeeper uses this data system to serve cold reads from this data file system, which is also known as a data device. Here, we should know that unlike other messaging systems, Bookkeeper does not open a separate dedicated file for each topic. Rather, Bookkeeper keeps only one journal file and one entry log file open and writes all incoming messages coming from different topics to the journal file and the data log file sequentially. So Bookkeeper always performs sequential writes and aggregate data from different streams to one data file. And at the same time, Bookkeeper also maintains indexing to store the offset of messages which are there in the entry log data file for faster cold reads. So now, as you can see in this diagram, it has three major components: journal, entry log, and indexing. Now, in the right side of the diagram, we can see that when a writer writes the message into a ledger, Bookkeeper first adds the message into the write cache buffer, and then it writes the same message into the journal file system. And then it syncs the entry to the disk, and then immediately sends the acknowledgement back to the writer. Now, as we can see in the left side of the diagram, Bookkeeper has asynchronous task running in the background, which sorts the data from the write cache, and then syncs the data to the data device. And then we can see the third box, which is index. Bookkeeper also has an indexing component which manages index of entries which are there into the entry data log file. Now, looking at this design, the question arises, why Bookkeeper needs to perform dual write? Because in general, most of the real-time application, consumer read the data from the cache only. So why do we need dual write? One in journal device and other is the data device. And why do we need such IO isolation in Bookkeeper? Well, in normal conditions, consumers application don't have a backlog and they read the data from the cache only. However, if consumer is slow or it comes back online after a while, then it builds a huge backlog of messages which have been edged out from the in-memory cache, and then it forces the system to read out the data from the disk storage device directly. And in a multi-tenant systems with a scale of large number of topics, having backlog for multiple topics is a very much relevant scenario. In that case, backlog draining for multiple topics force the storage system to read the data randomly across all various entry log files, which eventually degrades the device performance, and it could also lead to IO thrashing, which can cause patch cache, swap in and swap out. And that can also be worse if the same IO storage component is shared between the write path and the read path. And in that case, backlog draining can directly impact the write latency. However, in Bookkeeper provides a clear IO isolation between the write path and the read path. So cold reads happening from the data device will not impact the journal device at all. So like backlog draining will not impact the write latency. So now we are familiar with Pulsar IO isolation with two separate devices, journal and the data device. So in the next couple of slides, we are going to talk about how Pulsar has adapted various technologies to get the best performance out of them. So this slide shows the Pulsar's journey in Verizon Media, where we had deployed the first release of Pulsar in 2015. And then with the time, as technologies evolved, Pulsar has adapted new emerging storage technologies seamlessly to improve the storage performance over the time. This slide is an example of Pulsar adaptation with storage evolution. So as we can see in the diagram, in 2015, The first generation of Pulsar was using 2 separate hard disk drives with RAID 10 controller, each for journal and the data device. The advantage of hard disk drives they are economical and good for sequential writes. However, they have a lower random IOPS, which are mostly used by backlog draining and updating the index on the data device. In the next generation in 2016, we had upgraded the journal and data device with SSDs. SSDs provide higher random IOPS compared to hard disk drives, so data device can leverage higher random rates to drain the backlog faster. We had also enhanced indexing of entry log data files from interleaved index file to the RocksDB for better performance and to reduce random IOs done on those index files. We are going to discuss this in details in the later slides. Then in 2018, we used NVMe. At that time, NVMe was gaining the popularity because of its better performance and higher throughput compared to SSDs. We have used NVMe for journal and data devices both to get the higher throughput on journal and better random reads on data device. And now in 2020, we tried out persistent memory, which is the highest performing, ultra fast and expensive storage device right now in the market. Persistent memory provides a non-volatile storage at nearly memory speeds. Use of persistent memory in Pulsar gave us 5 times improvement without adding any much cost overhead. We are going to discuss each milestone in details in the later slides. So this is the overall glimpse of Pulsar's journey in Verizon Media in last 5 to 6 years. Now with this experience, we would like to share Pulsar's performance in details with these different types of storage devices. And we'll also see how beautifully Pulsar can adapt any kind of storage device to squeeze best performance out of them, and how some of the latest technologies like NVMe and persistent memory, those can be leveraged at a very low cost overhead. So now let's start with the very first device, which is the hard disk drive. As we know, from the 80s until a couple of years ago, database systems have relied on magnetic disk drives as a secondary storage. The primary advantage of hard disk drives are affordability from a capacity perspective. It also gives a reasonably good sequential performance, but it provides a lower random IOPS. Bookkeeper writes write-ahead log into journal device sequentially, which is an append-only structure. Bookkeeper also writes sequentially on data device while storing data from write cache to the entry log files. So hard disk drive with RAID 10 controller can be a great fit for sequential writes on both journal and data devices to achieve reasonably good write throughput with a lower latency and of course with a lower cost as well. However, hard disk drive provides pretty low random IOPS, and one of the reason of slowness in the hard disk drive is seek times. Bookkeeper uses most of the random IOs for the backlog draining and updating the index files. So in order to reduce random IOs by Bookkeeper, in Bookkeeper we made an enhancement in indexing by replacing the interleaved index file with a RocksDB. So with the index file, one of the major issue was Bookkeeper was creating one index file for each ledger, and it performs random IO while updating the index. Now in Pulsar, Bookkeeper has one ledger open for each topic. So with large number of topics in the system, Bookkeeper has to open large number of file descriptors in the system and perform random IOs across those many index files, which can really impact the Bookkeeper performance. So to address this issue, we used RocksDB to store index of entries which are there in the entry log files. RocksDB is a log structure based embedded key value store. Bookkeeper uses RocksDB as a Java library within the Bookkeeper process, so it does not provide any, it does not add any additional complexity, or it does not need any additional operating efforts as well. However, on the other hand, the advantage of using RocksDB is it provides a low write amplification while storing the index, and it also reduces random IOs while accessing the index, and it also provides a better compression, which takes a very small storage space of the data device. So RocksDB helped us to improve overall data device performance and also reduce the complexity by removing the need of managing large number of interleaved index files in the system. So that was a great win for us to reduce the number of random IOPS and the complexity on the data device. Now let's talk about the SSDs and NVMe. So as we have seen, one of the limitations with hard disk drive for the data device was hard disk drive provides a lower random IOPS. SSD speed wins because it provides the higher number of IOPS. SSD do not have any moving parts, so there is no physical SIC limits. So SSDs are faster for reads and writes both. And NVMe is a similar technology as SSD. It also uses a NAND chips technology in it, but it is faster than SSD because it directly goes into the PCI bus and talks to the processor directly. And another reason why NVMe is faster than SSD because NVMe has a higher number of IO queue size, and each queue can support 64,000 queue command, which can give significantly higher throughput if we fully utilize all IO queues with parallel IO or the multi-threading. Now, the good news with the Bookkeeper is Bookkeeper has this capability to perform parallel IO on journal device by configuring multiple journal directories. So Bookkeeper can write into multiple journal files concurrently, which helps to achieve parallel IO on NVMe, and that ultimately leads us to get the maximum throughput out of NVMe device. So using NVMe for journal device helped us to achieve 2 to 3 times of throughput improvement with a low latency. So as you can see, this is another good example of Pulsar's adaptability to squeeze best performance out of the device based on the device characteristics. Now let's look at the quick comparison between the random and the sequential IO between those storage devices and understand their impact. However, in Bookkeeper, we mostly care about sequential writes, which are happening into journal and data device for throughput, and the random reads, which are happen for the cold reads. So let's focus on the red bar, which is the sequential write, and the yellow bar for the random read. So here we can see the very good improvement difference between hard disk drive and the SSDs, especially with the random IOs. And if we compare SSDs and NVMe, then NVMe gives 2 to 3 times higher throughput compared to SATA SSDs. However, if we see the last device in the graph, which is the persistent memory, it is a clear winner. It outperforms any other storage devices in the market. In the latest slide, we are going to discuss about the performance or number of Pulsar with all these different persistent storage devices. But before that, let's discuss about what is persistent memory and how can we use in Pulsar to achieve higher throughput without adding much cost overhead. So the reason why persistent memory is faster than other devices or NVMe, because persistent memory directly talks to the processor over the memory bus, unlike NVMe, which has to go through or PCI bus. So going through memory bus directly means low latency, higher bandwidth, and much higher throughput. So this is a very quick visual comparison between different storage devices in terms of cost and performance. So if we go up in this pyramid, we can achieve a higher throughput and better performance, but it also increases the cost, right? So now we know that persistent memory is the highest performing storage device in the market, and it is also a very expensive device compared to all other persistent storage devices. So therefore, it should be used for a use case that is write intensive, and at the same time, it demands a very small storage space to achieve maximum throughput out of it, and it adds minimum cost overhead. Bookkeeper is one of the good example for this use case because Bookkeeper journal is a write intensive, and it also stores the short-lived transactions logs only, which needs a very small amount of storage. So we used persistent memory for journal device. So after using persistent memory as a journal device in Bookkeeper, we achieved 5 times more throughput by maintaining consistent low latency, write latency, which is 5 millisecond 99 percentile. Also, adding a small size of persistent memory for journal device doesn't add much cost, which is even less than 5% of total Bookkeeper cost. So it shows that Pulsar's architecture can nicely adapt any next generation storage technologies by achieving significant performance improvement without breaking the budget. That is the most important thing. By saying that, I would like to emphasize that it's not easy for all the system to adapt different storage solutions in such an efficient and the cost-effective way. Bookkeeper's architecture is based on write-ahead logging, which is a very old technique used by database for a long time, and that actually gives the opportunity to Bookkeeper to use persistent memory for low-cost write-ahead logging, And that makes a difference with other messaging systems which don't use write-ahead logging because of that, the system cannot adapt the persistent memory in a very cost-efficient way. So now let's quickly check out the numbers and see Pulsar's performance with these various storage devices. So in this graph, the right side, we can see on the y-axis, on the chart shows the latency in the millisecond, and x-axis shows the throughput in megabytes. Now, remember, in Verizon Media, while doing this performance testing, we have to consider that most of our use cases are very latency sensitive. And the SLA for all those use cases are 5 milliseconds for the 99th percentile published write latency. So we are basically comparing all the throughput with the low latency only, which is around 5 millisecond of 99th percentile. So if we see for the hard disk drive, we can see that we can achieve this 5 millisecond SLA with throughput around 120 MB. With SSD, we can get the throughput nearly around 200 MB. With NVMe, we can go up to 350 MB. And then with persistent memory, we can just go up to 600 to 650 MB. So, however, I would like to call out two things here in this performance number. First, in order to give persistent guarantee, Pulsar does fsync on every published message, and then only it sends the acknowledgement back to the publisher. So Pulsar gives persistent guarantee and does the fsync while doing all these performance numbers. And while measuring the performance throughput, we were also doing the cold reads by draining the backlog, which gives a very clear picture how beautifully Pulsar can manage IO isolation and makes a perfect example of multi-tenant system. So unlike other messaging system, Pulsar can support different types of use cases on the same cluster. Now we have discussed Pulsar state of art with Pulsar's throughput performance. So in this slide, we are going to talk about recent migration of one of our large Kafka use case in the Verizon Media, which basically where we migrated from Kafka to Pulsar. We are going to mainly discuss about cost difference and the different feature parity that motivated the team to for this migration. So in Verizon Media, we have a monitoring system which was using Kafka messaging for the use case. For this use case, the team was managing Kafka cluster with 33 brokers to serve around 3 gigabyte of published throughput. And this use case also has cold reads as well. We migrated this use case to Pulsar with a cluster of 10 bookies and 16 brokers. Here, we should know that Pulsar broker is a stateless component, and it does not require any storage on the host. So Pulsar broker cost is less than 1/4 of the cost of bookie host. And we have also seen in the previous slides that bookie with persistent memory as a general device can give 5 times more throughput improvement, but it also adds the less than 5% of total cost of bookie. So with a Pulsar, the total traffic can be handled, by half of the resource of what Kafka cluster was having. So cost is one of the major motivation for the system to choose the right framework to serve the purpose. And having cost-effective infrastructure was one of the major motivation for the team to migrate from Kafka to Pulsar. Other than cost efficiency, team also had motivation to use few Pulsar's feature which are not available or not very well supported in Kafka. We already talked about the throughput and the cost. Apart from that, one was the geo-replication. So Pulsar provides out-of-the-box native support of geo-replication from day one. Pulsar brokers replicates the message asynchronously and reliably across the clusters, whereas Kafka provides a standalone tool like Mirror Maker.
Rajan, be mindful of the time.
Oh yes.
Got about 1 minute, Rajan, and I do see questions coming in here, but you got about another minute. I say another minute or two. It's
sure,
fine. Okay.
Sure. And the queuing, which is kind of not very well supported in Kafka, where Pulsar does it from the day one. So these are the main major motivations for the team to actually move from Kafka to Pulsar. Now, Joe is going to talk about what are the future efforts that we are going to make in Verizon Media for the Pulsar.
So I don't want to spend a lot of time on this, but we plan to do a lot more with the persistent memory. Completely bypass the file system, and get even higher throughput. We also plan to use extensively tiered storage for because tiered storage in Pulsar, which is inward, works very well, with some of the use cases we plan to, onboard in the near future. That said, I'll leave it open to questions.
Excellent. So Joe, Rajan, if you look at the Q&A box on your screen, you will see that we currently do have some questions there. If you want to go ahead and read them out loud, answer them out loud, do you see them?
Okay, so I have one question here, and the question is, with PMEM, how are the entry log writes able to keep pace with higher throughput writes happening to the journal? Okay, so the entry log writes are asynchronous, and it's only one entry log. I think most people have this misconceptions that, because a storage node writes it serves multiple topics, there are multiple files getting written all through it. That's not correct. The entry log actually multiplexes all topics served by that bookie into one single file. So it's just sequential writes going to, the data devices. And, it's asynchronous, it is batched, the entries are sorted, because persistence guarantee is given by the journal writes. And, the entry log writes are highly optimized, in terms of, for throughput and IOPS. So that is something which Bookkeeper has the luxury of doing at its own pace. And the Bookkeeper architecture ensures that there is only one file that is getting appended to. I don't know whether that answers the question or not, but if you have further questions, I'll be open to answering it.
Yeah, folks, if you have any other questions, feel free to drop them in the Q&A box. We've got about another 4 minutes or so to do Q&A. So let's see here.
We'll be talking a lot more about, the details of how we operate in the system in a talk tomorrow.
Another question here, Joe, that just popped up.
Okay. Does Bookie support compacted-based topic? I think.
So Pulsar does support the compacted topic. Pulsar has the feature. There are some use cases, like a database use case where you would like to keep only the recent key for every recent key for every messages. So in that way, you can always do a compaction. So the answer is yes, Pulsar does support the compaction of the topic.
Okay, the next question is, are there ordering guarantees in data entry? Yes, ordering guarantee is there per writer. Per writer, that is, per writer, Pulsar guarantees, message ordering.
All right, got a couple more minutes here. These are all very good questions. And Joe, I know that you're going to be doing a blog post about this presentation, going more in depth, but I'll let people know about that a little bit later as well.
Yes, we'll be publishing a more detailed, in-depth, kind of blog about, how we went about, implementing this whole persistent memory system and, what are the numbers behind it. That will have a lot more details.
So I guess a question that I'd love to ask, looking at sort of the industry, there's claims that Pulsar has, significantly higher complexity. We're talking more servers. We're talking that, it's harder to operate. And it's much harder to do than, say, Kafka. What are your thoughts on that? That's definitely a trending topic right now in the industry. Thoughts, Joe, Rajan, anything you want to say about that?
So I think, and this is a loaded question.
It is, I know, but I thought, hey, it's timely. It's timely based on what folks have been chatting.
Yes. So there are two concepts out there, which I would, like to kind of clarify on. One is, okay, there is this separation between storage and compute, and you require double the number of servers to run Pulsar. And I think that is a very presumptive question in the sense that it assumes that you need one storage node in Pulsar to serve what a broker does in Kafka, and that's not correct. I think we have just presented the numbers here, right? Because ultimately, what matters is not whether you run a different number of servers. It's like how many in total would you need? That's the real question. For a given workload, how many in total would you need, and what does it cost? Right.
Yeah.
So it's not an apple-to-apple comparison when you say you need double the number of servers. Yes, that just assumes that one from there is equivalent to 2 over there, which we from experience know, and it's not correct.
All right. All right, Joe, I want to be mindful of time since we've got so many additional great presenters today. So what I want to do is I just want to thank you and Rajan both for your time today. I see you've shared a slide here with your email addresses. Folks, if you want to reach out to Joe or Rajan or connect with them on LinkedIn, please feel free to do so. As mentioned, they will be writing a very in-depth blog post about their presentation. If you'd like to know when that's live, please go ahead and follow Yahoo Developer Network on Twitter, which is just YDN. And I'm going to go ahead while we're here, and I'm just
there is one more question here.
Sure.
I'm not clear on.
I just see. Yes, one more popped up. Okay, go ahead, Joe.
Order of the task can be managed by workflow, etc. I'm not exactly clear on what is being asked, but like if you want to manage an ordered queue, yeah, Pulsar can definitely provide that. And we have people who use that is one of the use cases we support within Verizon Media, that to schedule workloads to run. It's basically background intensive jobs like image processing or which is cropping. That is one of the workloads that we today support within Pulsar.
All right, and I think that's it for questions, but I am seeing a nice note here. Thank you to SD for sending a note that said great talk. Obviously, this will be made available on YouTube. So just to quickly recap here, Joe, Rajan, thank you so much. I'm going to go ahead real quick and stop recording. Folks, do stick around because at 11 o'clock, we will have another great presenter. Let's see here. We'll have Pulsar Functions Deep Dive with Sanjeev, who I see is already on the line. So thank you very, very much. I would love to just clap for you real quick. Thank you, Joe. Thank you, Rajan.
Thank you very much for all the attendees. Appreciate your
Awesome.
time, and please reach out to us if you have questions and follow us on YDA.
Thank you so much.